Right. In the last time we talked about the cosmological perturbations in the Newtonian gravity. So the we use the Bohr quantity, the energy density, plus velocity as a quantities in the fluid mechanics, and this represents the matters, and additional there's some more quantity, gravitational potentials, which is represents the gravity. So we will generalize these cosmological perturbations from the Newtonian gravity to the general relativity theory (GR). So let's review Soron's Newtonian gravity just a moment. So that we define the density perturbations deltas as a ratios of the fluctuations over the background, and that density perturbation satisfy the following equation of motion. So we can determine the evolutions of the delta. So that's a quite the typical form of the harmonic oscillator form, but there are a friction term from the expansion effect because we consider expanding universe, and we define the speed of the sound, which is the coefficient between the project fluctuations and energy density fluctuation, and in the right hand side there's a gravitational potential term. So we can find some specific wave number, and the corresponding is the wavelength is called the Jeans wave number. And if the scale is larger than the Jeans wavelength, then that density perturbation delta is growth exponentially through time. So it is called the Jeans instability. And we apply the such a density perturbations for the case of the matrix, and this case is only hold for the non-relativistic case. And we devise the three dominant eras of the history for the universe. So the results of the evolution of, for the matter fluctuations are different for each era. Such a delta m the only grows for the matter dominant era, but for the radiations and dark energy dominant case, the matter fluctuations does not change much. So today, we will discuss the cosmological perturbations in the general relativity theory. So the first of all, the gravitational potential pi should generalize to the metric tensor, and also the energy density, projects, and the velocities should be generalized to the stress energy tensor. And we will insert the such a metric tensors and the stress tensor with the first order fluctuation, and we'll insert to the Einstein field equations eventually. So the perturbed space-time can be decomposed by the background part and the fluctuation part. The background part is given by the FRW metric, and we only consider the burst linear order fluctuation, and there can be some several fluctuation, plus the temporal part, and the cross term of the spatial part and temporal part, and the spatial part. So that is given by the vectors and is given by the tensor. And we can decompose of the such a scalar vectors tensor again is called SVT decomposition by imposing some specific condition like the divergence last or twice last such thing. So both of the vector we can decompose the one scalar part and the one vector part. The scalar parts are given gives the vector component by the gradients of the this scalar quantity, and the vectors quantity satisfy the divergence last condition, so that degree of freedoms in here is only the 3. And similarly, so we can do the similar process for the tensors. These tensors rank 2. There are 2 index, and this is a symmetric. So there's a positive of the scalar here, and the positive of the vectors here. Some of the notations that defined here, and the binary parts are tensors, and the tensor satisfies the 3 conditions. divergence loss and the trace loss conditions. So if we count the degree of freedom for each scalar vector's tensor decomposed part, for the scalar part, they are with the ball degree of freedom from the original scalars, and the B comes from the BI, and the CE comes from the tensor part. And for the vector part, the BI has a 2 degree of freedom. There are one divergence loss conditions, and also for the EI there are 2 degree of freedom. So total degree of freedom is 4. And for the tensor part EIJ, there's only the partial inductor and the symmetric, so that there are 6 degree of freedom. And if we consider divergence loss conditions and anti-loss loss conditions, then only the remaining numbers is 2. So the total number is 4 plus 2, it means 10. So it corresponds to the symmetric length tensor. Under each scalar vector's tensor fluctuations that mix each other's Abel's order. Under the case of the vector's fluctuations, it decays quickly and not produced in the impulsion, so that we do not discuss here. And the case of the scalars and tensor perturbation, it will be related with impulsion. And there are some quite too many degree of freedom. So by using some specific choice of the gauges, we can remove some of the degree of freedom, and that's just physically redundant. So we can consider the following gauge transformations as coordinate changes. The QC includes the temporal parts and the spatial parts like that. And for example, if we consider such a coordinate transformations, then for example, the scalar perturbations A changes like that. It is just step by step. There are just burst order Taylor expansions here, and also burst order expansions. And if we define A tilde as a transformed quantity, then this gives the we calculate all the things. This term gives this one, and this term gives this one as a definition through the Hubble parameters A prime sub A, where the prime is the time derivatives for the component time. So the A tilde the gauge transformed quantities as given by such a form T primes and some of the Hubble expansion, where the T is the some coordinate transformations to the temporal parts. And similarly, we can do the same thing for the other quantity, like the other scalar BCE and the other vectors quantities, BIEI and the other tensor quantity. And by defining the combinations of some specific quantity, we can find the gauge invariant terms. So the EIJ is the EIJ is the gauge invariant is up, and we can bound some scalar quantities to psi pi as the linear combinations of A, B, E, such a thing. And here so we will use some specific gauges, which is B and E is equal to 0. And we'll define, in this case, the A and the C are just given by the psi and the minus pi. And in the abundance of the anisotropic stress, the potential of psi and the pi is the same, and the pi actually represents the gravitational potential, and we discussed what is the meaning of this pi. And the second step is the perturbed matters for the stress tensor. Similarly, there are a background part and the fluctuation part. For the perfect flow is the stress tensor satisfied the following form with the ball velocity and energy density and pressures. And similarly, for the fluctuations, we consider the burst order. Burst order here, so for the energy density and the pressures, and the burst order for the ball velocity and burst order for the pressure. And there will be the anisotropic stress, but we will ignore here. So here is some overall point of view from the Newtonian to the general relativity theory, G mu and T mu. And here's we want to bounce the we want to find this the ball velocity in terms of some expansion impact. So the ball velocity satisfies the following condition for the full orders and the zeroth order. So for the first order, the perturbations of the fluctuation of the matrix and the fluctuation of velocity satisfy this relation, and that's just the contractions of the tensor index. Then we can find by using the ball velocity and its co-factors is given by some scaling factor, and we can insert to the ball velocity part. Then we can bounce the fluctuations of the ball velocities that are given by the functions of the expansion effect, so and also the scalar perturbation. So that we can find the total ball velocity as which decomposed by the background part and the fluctuation part. It contains the scaling factors and the scalar perturbation and the smooth velocity, which is defined by here. And similarly, we can find the explicit form for the ball velocity with the Q-factor form by using the matrix tensors here again. We just lowering the index by using the matrix tensors, and the matrix tensors contains some scalar perturbation, so this gives such a form. So this is just a process of the ball velocity in terms of the scale factor and scalar potential, and by using that we can find the stress tensors, fluctuation of the stress tensors in the first order. We insert the ball velocity here, this term, and we only consider both linear order. Then we can calculate what is the each terms of the stress tensor fluctuation components represents. Supposed to the 0, 0 components represents the fluctuations, and density, and the I0 components is correspond to the momentum density. And we will set the b equal to the zeros as a gauge choices. So the 0j components are actually same with ij component, and ij components gives the project fluctuation. So now we are ready to insert the fluctuations of the t menu, stress tensors, and the fluctuation of the z menu to the Einstein field equation, and I will discuss it in the next video.